Hello, everyone. Our presentation's title is Identification and Analysis of Health Vulnerabilities in Los Angeles. My name is Jeffrey Marin.
I'm Leonard Garcia.
Jacqueline.
Anle.
All right, so we can start with our problem statement. What we want to do is better understand the health of our local communities in the city of Los Angeles. In order to do so, we're going to focus on a few of the health issues that we have. And in the last few years, there's been the COVID epidemic that we've been worrying about. So we want to definitely focus on COVID, specifically COVID case rates, as well as COVID death rates. And there's a few other health issues that we want to focus on as well, such as low birth weight, asthma, as well as cardiovascular disease. Our project overview, there's three major results that we have for our project. The first being identifying vulnerable communities, which we try to basically identify high pollution groups that have the highest negative health rates. Next, we actually conducted some statistical inference in which we found some of the top features that are correlated to COVID case rate and COVID death rate. In the end, we tried to actually find some predictions. So in order to do that, we use some machine learning to find the best predictive models for our health problems. For our project dataset, we actually merged two different datasets, the CalEnviroScreen 4.0, along with the COVID data from GeoHub. Now, this CalEnviroScreen data is a tool for identifying communities impacted by different sources of pollution. And it actually uses 21 different indicators, which includes socioeconomic, health, as well as environmental data. And that COVID data is from the city of Los Angeles. As you can see here, this is a CalEnviroScreen model. It's split up into two different parts: pollution burden, which consists of different types of exposures, as well as environmental effects, and population characteristics, which are sensitive populations, as well as socioeconomic factors. And as you can see here from the heat map of, this is a CES 4.0 score percentiles for Los Angeles. We can see a lot of different cities fall in some of these vulnerable zones. So these higher score percentiles, 90 to 100, are in red. You can see cities such as Gardena, Compton, Linwood, even Bell and Vernon, they fall in these high risk zones. So we're gonna pass it over to Leonard so he can give us a little bit more information on these vulnerable communities.
Hello, everyone. My name is Leonard Garcia, and I'm going to talk a little bit more about identifying vulnerable communities in Los Angeles. All right, so to identify these vulnerable communities, we began by looking at the areas of high pollution. So specifically, for every pollutant in our data set, we defined high pollution areas as those that fell in the 90th and above percentile. And then for these high pollution areas, we calculated the average rates of adverse health conditions that we had in our data set. And then after we calculated these averages for the high pollution areas, we calculated the averages for all of Los Angeles, and then we compared the two. So as an example, if we look at the rates of emergency department visits for asthma, we see that the average for Los Angeles as a whole is about 57 per 10,000. But when we look at the areas of high pollution, we see noticeably larger average rates. In this chart, we listed the areas of high pollution with the largest averages. And we see that the group with the largest average, the group that consists of areas with high concentrations of chemical emissions, we see that it had an average rate of asthma about 1.5 that for Los Angeles as a whole. And as we repeated this for our other health conditions, we saw a similar pattern emerge. There were 3 high pollution groups that consistently had the highest rates of our adverse health conditions. And these 3 high pollution groups were areas with high concentrations of chemical emissions, areas with high potential lead exposure in children, and areas with large amounts of contaminants in the drinking water. So what we did is we defined vulnerable communities as those that belong to all 3 of these high pollution groups, and then we focused our attention further on these vulnerable communities. So when we looked more closely at these vulnerable communities, we found that the average rates of our adverse health conditions were much higher than the individual high pollution groups, and even higher still for Los Angeles as a whole. For every one of the health conditions we had in our data set, these vulnerable communities had average rates that were significantly higher than the average rates for Los Angeles. As an example, the rates of asthma in these vulnerable communities were almost double were those for all of Los Angeles, and the same we found for all the other health conditions. So just summing up the past couple of slides, we found that areas with high combined concentrations of chemical emissions, high potential lead exposure, and high levels of drinking water contamination were particularly vulnerable to adverse health conditions. When we compared these vulnerable communities to Los Angeles as a whole, we saw that the rate of every one of the negative health conditions we had in our data set was significantly higher for the vulnerable communities than for Los Angeles as a whole. Okay, and then so now that I've talked about the vulnerable communities, I'm going to pass it over to Derek to talk about some correlation testing we did.
We use statistical inferences to find features that most correlated with COVID case and death rate. The results are conducted based on a bootstrapped dataset of 10,000 samples. All results obtained through our tests have a p-value less than 5%, making them statistically significant. The following features are highly correlated with both case rate and death rate: lack of high school education, percentage of population living in poverty, potential risk for lead exposure, and percentage housing burden in low-income households. We observed that these features are highly correlated with the population's socioeconomic status. The correlation with the percentage of the adult population with less than a high school education is indicative of the effectiveness proper education has on the individual's COVID protection measures. The percentage of the population living in poverty points to a financial burden as a probable cause of escalating high-risk behavior. That exposure is highly income correlated, but we suggest additional research to be done on the effect lead itself may have on catching and treating COVID. For features more correlated with one statistic over the other, a feature with a high correlation to case rate was a number of emergency department visits for asthma. The feature that most strongly correlated to death rate was a percentage of limited English-speaking households, hinting at the lack of proper communication channels as an important detriment to receiving the necessary COVID treatment. Overall, we found that education, health, and socioeconomic features showed a strong correlation to case rate. For death rate, it was predominantly socioeconomic features that showed the strongest correlation. This may imply that available COVID treatments are very effective, but populations with low socioeconomic status are having trouble accessing adequate treatment. Our correlation tests also found that the Hispanic population is most at risk of COVID cases and deaths, whereas white, other, or multiple ethnicities and elderly over 64 were least susceptible. From these results, we believe the implications are that education and financial stability are among the most important factors in identifying vulnerable communities, and we heavily suggest the necessity to commit more resources to facilitate communication with foreign language speaking households to improve their COVID treatment. For suggested future studies, we are interested in the socioeconomic conditions that led to increased vulnerability among Hispanic population and the investigation of the potential effects lead exposure may have on COVID vulnerability. And next, we will present our predictive models.
So with everything, we're using machine learning to make a predictive model on those health issues. So for our data, since we combine the scout environment data with COVID data, we have those data. We split in 3 different data types. So we're using raw data type as the actual value of measurement of the pollution, and then we have normalized data, which is we normalize all the raw data between 0 and 1, and the in the CalEnviroScreen data, they have the percentile column, which is ranking all those pollution value and ranking them between communities. So we only using those percentile value. And we're using root mean square error as a measurement between the predicted value and observe it to see which one have better performance. And since our data set is so small, we're using K4 cost validation to estimate the performance of our model, and we're using 5-fold cost validation, which is 80% as training, 20% at testing. So this is the result when we apply multiple model. So we have 4 different model that we running with regression, lasso, XGBoost, and random forest. So at the result of this, for case rate, the mean of the case rate we have 25,000, and with the normalized data in the red box, we able to predict is at 3,365 different, which is about like 15 to 20%, 15% error different. And to sum it up, we select the best feature for best model with the best data type. So in this case, for case rate, we found lasso regression on normalized data, and for that rate, we found random forest on raw data. But with this one, we have like 50% inaccuracy. We can think it's based on because we didn't use case rate as one of measurement to predicting that rate. For asthma, we have lasso and good regression on percentile data, cardiovascular disease, XGBoost, and random regression on percent data, and low birth weight, we have random forest on percent data. So most of our accuracy model is using from the percentage data. So possible future work that we actually can do is we actually change the pollution measurement, which is we change it increase or decrease the pollution to actually estimate the health issue in that area. And we can actually incorporate additional data set such as like cancer and other diseases to actually make to actually apply machine learning to make the prediction model for those. And for acknowledgement, we give thanks to PicMath to actually make this project to be possible. We give thanks to Dr. Yi for a professor at Cal State LA for helping an advisor helping us with throughout the whole project. We give thanks to Eva Pinard, Chief Data Officer from City of Los Angeles, because for helping us with data set and guiding on how to do the project. Thank you.